Now we'd like to look at a slightly more complicated circuit, which is what we call a multi-loop circuit. Suppose we have an EMF, and we have a resistor R1, we have a resistor R2, and we have another resistor R3. Now, to make this a little bit more complicated, I'm going to put a second seat of EMF in. I'm going to call this one E1 and this one E2. And I like to analyze this circuit. Now, we're going to use the same ideas that we've done before. Notice we have two junction points. And so first we assign currents in the branches. I'll call this one I1. I'll call this one I2 and I3. And here we have a very simple example of current conservation, that the current that comes into a junction is equal to the current that goes out. Now notice we have two junction points. And the current that's coming into this junction point, you can call this A and B. The current coming in is I2 plus I3, and the current going out is I1. So we have actually the same equation, which is a general rule that if you have n junction points, you have only n minus 1 independent current conservation equations. Now, the next thing we want to do is we have loops. And so let's do some circulation. So we have a circulation direction here. And I'm intentionally going to choose a circulation direction the opposite way there. And I have two loops. And so I want to do Kirchhoff's law of the sum of the voltages around a loop is 0. So we start to write them out. We cross the battery from the negative to the positive terminal. So we have plus E1. We're crossing the resistor in the direction of the current, minus I1 R1. We're crossing resistor 2 in the direction of the current, R2. That's our first equation. And our next equation is, let's start at any point. So let's start at point B. Notice that we're crossing resistor 2 opposite the direction of current 2. So that's plus I2 R2. Now we're following this branch of the circuit, and we're crossing resistor R3 in the direction of the current. So that's minus I3 R3. And now we're crossing this seat of EMF from the positive to the negative terminal. So we have minus E2 equals 0. And these are our circuit equations. Notice that in this problem we have three unknowns, which is often the case. I1, I2, and I3 are the unknown currents in the branches. And in general, in circuits, we're building a circuit, so we know the EMFs and the resistance. We have three equations and three unknowns, and we can solve that algebraically. Now, you might have asked an interesting question. There's actually a third loop in this circuit, a loop going all the way around the whole circuit. Why didn't we include that? Well, let's write that equation out just to see. So in the outer loop, we have plus E1, cross resistor R1 in the direction of the current, cross resistor R3 in the direction of the current, opposite the charge, so that's minus E2, and that brings us back to where we started. So is that a new equation? Four independent equations? It's not. Because let's look conceptually at what we did. When we crossed this resistor, we crossed in this direction. When we went this way, we crossed in the opposite direction. So those have two signs. So if I added my two circuit equations, I'm essentially canceling this leg. Now let's just add equations 2 and 3. And what do we get? We get E1. We get minus I1. Here's where we're canceling the inner two pieces. And so if you add these two equations together, they cancel. We get the minus I3, and we get the minus E2. And that shows our second important idea about circuits, that if we have n loops, then there's only n minus 1 independent equations in this type of topology. And let's just remind ourselves that if we had n junctions, there's only n minus 1 independent current conservation equations, current conservation equations. And these are the sum of delta VI equals 0. And that's how we handle a multi-loop circuit. Now, I want to say one last thing when solving multi-loop circuit problems. We have three equations. There's many ways to solve algebraic equations. When I look at this system of equations, I like to choose one equation as a backbone. This one, I1 equals I2 plus I3. And the reason I choose that as a backbone is I see that in this equation, I can solve for I1 in terms of I2, so I can make a substitution for I1. And in this equation, I can solve for I3 in terms of I2, and I can make that substitution for I3, and then I can solve for I2. We now want to look at how we can take a complicated circuit where a lot of resistors are connected and start to simplify the circuit. We begin by considering just the case where resistors are in series. So let's look at something like this. We have a seed of EMF, we have a resistor R1, and a resistor R2, and it's connected in a circuit. Now, these two resistors are connected in series, and what we want to do is replace this circuit with what we call an equivalent circuit, where R equivalent, one resistor, and with a CD of EMF, the same current in both circuits. And in our equivalent circuit, we know that the E is equal to IR equivalent. And now we want to figure out how to relate resistors that are connecting in series to the equivalent resistance of this circuit. Now, the main idea here is that the voltage across two elements that are connected in series add. So the principal idea is that the voltage across the two circuits, which is going to be our EMF across these two elements, adds, and that's equal to delta V1 plus delta V2. So series elements, the voltage adds across them. Now, notice in our equivalent circuit, we have IR equivalent. And in each of these elements, we have Ohm's law, IR1 plus IR2. And so we see that when resistors are connected in series, and if we had many resistors in series, they add. And that's our first important way to think about decomposing a complicated network of resistors. Our second example of how to decompose complicated resistor networks are when two resistors are connected in parallel. So let's have a resistor R1, and let's have another resistor R2. Now, what does parallel mean? Remember that the potential difference across this resistor is actually equal to the electromotive force, and the potential difference across this resistor is also equal to the electromotive force. So that's what we mean by resistors. So here's our case of resistors in parallel. Now, again, what we want to do is we want to reduce this network to an equivalent network where we just have one resistor, R equivalent. And here the battery is putting out a current I. So that's the current we use here. There's the EMF. And so once again, now we have the relationship that the current is equal to the EMF divided by the equivalent resistance. Now, what adds in this case? Well, remember, if current is coming into a junction, we have current coming out of the junction. And what adds is really the concept of current conservation, that the current in, I, is equal to the current out, I1 plus I2. And that's our junction rule, because we're assuming charge is not building up at the junction. Now, once again, you can see why we've written it this way. The EMF for the equivalent circuit, the relationship between resistance and current is given by E over R equivalent. And again, using Ohm's law for the individual elements. So what's the same here, parallel, is the EMF. What adds is the current. And we conclude that when we add resistors in parallel, they add inversely. If we had more resistors, that would be our law. And that's how we handle resistors in series and in parallel. Here's our parallel case. Let's look at how we can decompose a network that consists of a number of resistors and batteries. So let's start off with something like this. We have a seed of EMF, E1. We have a resistor R1. Now here we have a resistor R2, and next to it a resistor R3. And next to that, in parallel, another battery, E2, along with a resistor R4, and the whole thing is connected. Now, when we look at this, our first principle is to see if we can make this network a little bit easier by looking for elements that are in series and parallel. Well, we can see that these elements here are both connected across the same potential difference. That potential difference is the EMF minus the drop there. And these two elements are also connected across the same potential difference. So we have three elements connected in parallel, but this has a battery. So these two elements we can reduce to equivalent element. We have 1 over R equivalent is 1 over R2 plus 1 over R3. And that tells us that R equivalent is R3, R2 over R2 plus R3 after a little combining terms in inversion. And so then our circuit looks like this. It looks like an EMF, R1, R equivalent, the second seed of EMF, E2, and the resistor R4. Now, at this point, you might ask, well, why can't we just say that R1 and R4 are in series? But they're not in the fundamental way that these two, this element here is in parallel with this element, and this resistor is inside that element. So the voltage drop across this element has these two terms in it, and you can't just say that R1 and R4 are in series. They're not in this type of network. We can't reduce this network anymore. So at this point, we have our conventions, and we can just set that up. We can say there's I1, I2, I3, a circulation direction, and we get I1 equals I2 plus I3, and we get E1 minus I1 R1 minus I2 R equivalent is 0. Going around this one, I'm crossing the battery in the opposite direction, no, in the same direction. So I get plus E2, crossing the resistor in the direction of I3. This one, I'm circulating opposite I2, so I have I2 R equivalent is 0. And that's how we can analyze this network. And we can only reduce it this far. We'd like to talk about energy conversion in circuits. So let's first consider a seed of EMF. And in this circuit, we'll just have a resistor. So this is some type of load. That resistor may even be something like a light bulb with a filament in it. Now, when we talk about power through a potential difference, remember that when you have the change of potential energy, when you move a charge, let's call it delta Q, across a potential difference delta V, represents the change in electrical potential energy. And the rate of changing electrical potential energy is what we call power. And if we divide everything by delta T, delta V, and we take a limit, which I'm not writing out here, this just becomes current times the potential difference. And that's what we mean by the electrical power generated. You can think of it this way, is that if you have something like a battery or wire, power can be put into the system or it can be dissipated in the system. Let's look at two examples. Let's begin by examining a battery. So in a battery, we have an EMF, and this is an ideal battery. And so what we can refer to is the power that the battery is putting in is coming from the electromotive force. Remember, electromotive force, that's some non-electrical force that's moving charges against the electric field. That represents the current that's running from the battery and times the EMF of the battery. Now, if the battery is discharging, then the battery is putting this amount of energy power into the system. And if the battery were charging, this would be the power that the battery is storing. So that's our first example. The second example is, let's look at a resistor. And we have a current in the resistor. And remember, current flows from the higher potential side to the lower potential. And so we can talk about the, let's call this V minus and V plus. Then when we have a battery connected in a circuit and current is running in this circuit, there is the electric field in the circuit is doing work on the charges, and the rate of doing that work is the power given by, so here, this is a power in the circuit or in the resistor, is given by the current times the potential difference, delta V. Now, this conversion of chemical energy, if it's a chemical battery, into electrical energy is the first step in the conservation. So what we could say is that the energy of the battery is equal to the energy in the resistor, and we have something like I times EMF equals I delta V through the resistor. And remember, from Ohm's law, in a resistor, this is I times IR, and if we cancel the R's, we get our circuit equation, which is just energy conservation. Now, let's think about what's happening in the conversion. As we know in a resistor that when electrons flow through the resistor, they're being accelerated by the electric field. That's the electrical work. So our first conversion is chemical energy goes to electrical energy. We are accelerating charges. Now, in the lattice of the resistor, there is collisions, and the lattice starts to vibrate. And what we see is that there's a dissipation of that electrical energy into what we refer to as thermal energy. This is the energy of vibration in the lattice. That means thermal energy means increase in thermal energy, the wire gets warmer.